I hope the screen is visible to everyone. Yeah. So, good morning, everyone. We are going to study in this lecture the finite difference method for option pricing PDs. I hope the screen is clearly visible and I'm perfectly audible. Let me quickly recap what we did yesterday because that was nothing but initiation of numerical methods. If any one of you have any queries, you can simply ask me. Uh, The idea is that we started numerical methods by telling you a reference book for numerical methods. That is Numerical Partial Differential Equation by J.W. Thomas and published by Spencer. We started with heat equation. There are two purposes. One, that it is simple to implement, and second, it is, I think, you must, I mean, most of you must have heard it at least before, right? So we took a heat equation, we understood its exact solution, what does it mean? And then we uh, understood that what exact solution means. Exact solution means that we can find the solution at any point, but numerically it is not. Numerically, we have to first define that point by grid, right? By making the grid. So we have made the grid and then we can find the solution on those grid points. I hope it was clear to all. And then what we did, we uh, took heat equation, we utilized the definition of partial derivatives that was we have been taught in our +2 course classes, and then we simply put the derivatives, the discrete version of the derivatives in heat equation, right? So this is the discrete version of the ut and uxx. Okay, so we can see here, and then what we did, we wrote the discrete version of derivatives, and then from figure, it is clear what points the solution is to be obtained. Then there is a smooth way that yes, you put n equals to 0 and y k equals to 1, 2, 3 because we need to find the solution only at 3 points. Okay. So this was the idea. Now k equals to 0, n equals to 0, n equals to 1, n equals to 2. This is how we did. Now we put all these values and we realized that, oh, we are getting a very, I mean, pattern full structure, right? It is not like random. There is a pattern. Okay, so we realize that the solution at first level, first time level, what do we say? Solution at first time level, that is that can be obtained easily by uh, just solving a system of equation. Just solving a system of equation. So I hope it is clear to everyone, and then we simply implemented it in MATLAB, and we found that yes, we got this V11, V12, V13, and similarly V12, V22, V32, and then V31, V32, V33. So it was not that difficult. Just to apply a loop, we will do the MATLAB also. So please anyone let me know, should I go for a bit of MATLAB or first I should tell? So okay, let us pose some challenges and then we'll go maybe for MATLAB, right? So or okay, let me first tell you the book. Some of you asked that the book. So this is the book you can follow, right? MATLAB, the language of technical computing. So for MATLAB, someone asked me yesterday that can you suggest one book? So the book you can, it is by MathWorks. So those who are not aware, this is actually MathWorks is the developer of MATLAB, right? The language of technical computing. Although it is very large book, you can see I have shown here to you the language of technical computing. This is of 900 pages, but it's okay. I mean, whatever you need, you can take from this, right? And so This is published by the MathWorks. Actually, the honor of tech. I mean, we can say the honor of MATLAB, right? So MathWorks is the website from where we get the MATLAB. So this book one can see, one can utilize for understanding the MATLAB, right? It's a wonderful book. It is very detailed, everything. I mean, this is like complete book, I would say. It is telling you functions, program, like arrays, multidimensional arrays, function handling, right? Everything it is given, right? So this is very simple book. One can, if you are interested, you can go with this. So this is published by MathWorks. Right, and it was published very early, like in 2000, around 2000, so you can easily get it. Okay, so now coming back to, I'll come later to the MATLAB, but first I'll pose some questions to you and to the community that, see, what we read yesterday, we took, so what we did, recap technically, right? So the idea is we took heat equation, we solved it using finite difference, approximations, right, of finite difference method. But there are questions. Who guarantees that whatever the solution you obtained is correct? Right. This is a very simple question. Very simple question, that whatever the solution you obtained, we obtained some solution, right? V11, V12, V21, V2. So who guarantees that it is correct? Right. So the challenge is for us is that how can we assure, can we assure that the solution obtained is correct? You might have obtained incorrect solution because you are doing something using finite difference approximation. So this is first challenge. Second, can we solve all the PDs by this technique? Right. This is also a question. Everyone, right? So they're simple questions. These are not very tough questions. This is very simple question, that how can you assure, how can you guarantee that whatever the solution you obtained, it is a correct solution, it is a accurate solution, right? And another one is that can you solve all the PDs by using this technique? So please let me know that any of you, like Aditya, Athav, Dipesh, Jaikishan, are you aware of these things earlier, or you are doing it first time? Anyone? I don't know actually. So I'm starting it from scratch. Maybe you are not aware earlier. So I'm starting it from scratch. The idea is simple, that we are going to read three concepts, right? No, you are not right. Okay, fine. Thank you. Thank you for your response. So we are going to read three concepts, right? So how will we assure it? So we are going to read three concepts. One is called consistency. We will not go in detail, right? It's just like to uh, to let you know that yes, theory is beautiful, mathematical theory is beautiful. It assures us that yes, whatever you are doing is correct. It assures us that yes, by this method you can solve other PDs also. Isn't it a good idea? Right? What is the good idea? That this theory, we will do some theoretical aspects, and we realize that, oh, if we can prove these things, we are sure that yes, whatever we are doing is correct. One is called consistency, then stability, and convergence of numerical scheme, right? So what is numerical scheme? The discrete version, right? The discrete version which you have written, that is called numerical scheme. And you want to check whether this numerical scheme is consistent, whether this numerical scheme is stable, and whether this numerical scheme is convergent. So I'm trying to tell you in a very layman way that uh, if these three properties are satisfied, we are sure that whatever we are doing, whatever we are going to get the solution, that is accurate, no need to worry. Please try to understand. For heat equation, you have exact solution. So you can compare your numerical solution with exact solution. But for other PDs, you don't have exact solution. So how will you compare? You don't have the option of comparing. So there, what is the idea? There, these three methods are life-saving. How? Because you check that your numerical scheme is consistent, your numerical scheme is stable, your numerical scheme is convergent. If you check all three properties, you are assured by mathematics that your solution, whatever you are going to obtain, is correct. You get the idea that why these properties are important? See, I'm emphasizing the motivation for these properties. Why do we need these properties? So suppose there is a PD whose exact solution is not there, right? No exact solution. Now you obtain some numerical solution. And since there is no exact solution, how you are assuring yourself that the solution which you are obtaining is correct? How will you assure? There is no way because there is no exact solution. Right? Then these three terms, right? These three proofs, these three concepts, they are going to help you. They are going to assure you that, okay, if you define a numerical scheme, right, and it is consistent, stable, and convergent, then you please do not worry. Your solution is accurate. I hope I'm clear, right? So we got the motivation for these three concepts because if there is no exact solution, how to know that our solution is correct? Our solution is correct. How to know? So there should be some mathematical properties who can assure us that okay, now your solution is accurate. Everyone understood? So finite difference method, we understood finite difference method for solving heat equation. We understood that okay, we can solve it. We studied yesterday that how to solve an EPD using finite difference method. But the problem is that who guarantees that the solution is accurate? Okay, let me give you a very simple example so that you can relate that. So all of us have been taught that if there is a semicircle, right? If there is a semicircle, any angle on the semicircle, what is its measure? Suppose you make this angle. What is the measure of this angle? Anyone can recall from class 7 and class 8? Anyone? No? Actually, it is 90 degree, right? If you recall from your earlier class 7, class 8, it is always 90 degree. But how can you assure? Because circle can be this is small, circle can be semicircle can be this is small, semicircle can be very large. So who assures you? Mathematics assures you that yes, angle in the semicircle is 90 degree, whatever the semicircle you take. Got it? Agree. So just like area of circle is pi r square. So who guarantees whatever the circle is? You see, whatever the circle is, whether this or very large, who guarantees that area will be always pi r square? Mathematics guarantees. So in the same way here, these three properties guarantees you that oh, whatever your numerical solution is, it is accurate. So I hope I'm clear till here. So now let me go one by one this property, right? So okay, so let me explain by the heat equation only. Let me explain, right? So first we will explain consistency. Please be clear that I'll not go in much detail, but I'll just give you the definition and how to prove it and what it is all about. It gives you actually, how it assures you that, how it assures you. Okay, so what is consistency? Let us see this heat equation only, right? So what we took here, this we so we know that if we take Vkn plus 1, right, minus Vkn upon delta t, this is nothing but del V by del t plus order of delta t terms. How many of you are aware by I mean from this notation? If you're not aware, then we can tell. So it is not very tough. Actually, it is coming from Taylor series expansion, right? So from it is coming from this equation 1, it is coming from Taylor series expansion. Taylor series, I hope everyone has read it, right? What it is? So we know that Vkn plus 1. What does it mean in our earlier notation? That this is Vk delta x and n plus 1 delta t, right? And how we can see this? We can see from here. You see, you see, if n is k is here, n is here. I hope everyone is comfortable, right? I hope everyone is comfortable, right? So now we have this. I'm looking at your chat also. So if you wish to express anything, you can write in the chat. So this, and how you can write using Taylor series, how you can write Vk delta x n delta t, this is comma, plus del V by del t at k delta x and delta t into delta t by 1 factorial, right? To delta t by 1 factorial plus del 2 v by del x t square k delta x and delta t into delta t square by 2 factorial plus and so on. So I hope everyone is familiar with this Taylor series. Now from this Taylor series, if you see that what you'll get, you just take, and what this is nothing but Vkn, right? We all know. So if we take this side, Vkn plus 1 minus Vkn, right? And we divide by delta t, both sides. So here this delta t will be cancelled out and here one power will be cancelled out. So what it will become? Del V by del t, k delta x and delta t plus del 2v by del t square k delta x and delta t into delta t upon 2, of course. So this is the term of order of delta t. This is basically this. Right, there is something, it is saying there is something multiplied by delta t. Okay, there is something multiplied by delta t. So all of us are comfortable with equation 1. All of us are comfortable with equation 1. Okay, so let me give 2 more minutes and then you will realize that what the consistency is. What the consistency is. So in the similar way, so what we wrote for del v by del t. Now we have to write for del v by del 2v by del x2 also, na? So again, what we need to do, that vk plus 1 n minus 2 vkn plus vk minus 1 n upon delta x square. This is nothing but equal to del 2v by del x square k delta x and delta t plus order of delta x square. That means what? If you expand it using Taylor series expansion, it is not that difficult. You can do it easily. If you expand this left-hand side by using Taylor series expansion, right? Expand it using Taylor series expansion, you will get on the right-hand side del 2v by del x2 and plus some terms of order of delta x square. And this is your equation number 2. This is your equation number 2. Right. Now, what you do, you subtract. So what was your initial original equation? Vt minus vxx, right? Vt minus vxx. So please tell me that if you subtract these both, right, what you subtract? You subtract left hand side and right hand side. Now subtract 1 and 2. What we'll get? The color. So what we'll get? Simply this Vt k delta x and delta t minus Vxx k delta t. This is Vxx, right? Vxx k delta x and delta t equals to Vn plus 1k minus Vn k upon delta t minus Vk plus 1n minus 2Vkn plus Vk minus 1n upon delta x square plus order of delta t terms and plus order of delta x square terms. So I hope till here at least I'm clear that if you subtract both, what you are getting? On the right hand side, you are getting order of delta t terms, order of delta x square terms. Agree? So then what is the idea? Now, what does it mean by consistency? Right? So just 1 minute. What does it mean by consistency? That if you take above delta t and delta x as tends to 0, right? Then this difference, this is, I mean, your continuous equation is equal to the discrete equation, isn't it? And this is what the definition of consistency is. Right? This is what the definition of consistency is. What is the definition of consistency? That we have seen, okay, everyone. What is that? Simple meaning. If you take, and what does it mean by delta t, delta x tends to 0? Okay, can anyone tell me? Delta t, delta x tends to 0. What does it mean? In our grid form. Anyone? In our grid aspect, what does it mean? Delta t, delta x tends to 0. It clearly means that you are taking a smaller and smaller and smaller step size. Suppose first you have taken 0.5, then you have taken 0.25, 0.1, 0.001, 0.0001, right? So what it says that if you take very small step size, your discrete equation is nothing but equal to continuous equation. This is what consistency is. Suppose it does not happen. Now think about it. Suppose it does not happen that whatever you have taken on this side and on this side, right? Suppose its difference is not giving you the exact equation. That means what? You have made some mistake. I mean, your scheme is not consistent, and therefore you should not expect accurate solution. Everyone, right? So what is the idea? Idea is very simple, that if this consistency property does not satisfy, then you should not expect, right? You should not expect accurate solution. Okay. Okay. So we can write in terms of norm also, and in terms of operator also, right? So let me write the definition. And this definition is from J.W. Thomas book, so which I have suggested to you, right? So the finite differences scheme, suppose we have the finite differences scheme, let me write it in a way that the finite differences scheme L K N G U UKN equals to GKN. Please do not be confused, right? It is basically your discrete equation, right? Is pointwise consistent, pointwise consistent with the PDE LV equals to F. So basically your PD is LV equals to F, UT equals to UXX, and its discrete version is given above. At any point, at point x comma t, at any point x comma t, if, right, for any smooth function phi, which is phi of xt, we have what we have, L phi minus f, right, at nk minus L k n phi k delta x comma n delta t minus g k n. This tends to 0 as delta x and delta t tends to 0. So let us not be confused. The simplest idea I would say, you can see from here, that as delta t delta x tends to 0, our discrete version and continuous versions are equal, and hence it assures us, what it assures us, that whatever we did, I mean this is scheme, please try to understand. What I said, that you take discrete form of continuous version, this equation 1. So this equation 1 is consistent. Why it is consistent? Consistent for the original heat equation, for this heat equation. If you take anything else, suppose you take UK plus 2 here, then it will not be consistent, right? Or if you take anything else, it will not be consistent. So what we realized, that yes, whatever the scheme we took, it is consistent. So we, at least one property is satisfied, that okay, whatever the numerical scheme we have taken, that is consistent. And so we expect that whatever the solution we will get, that will be accurate. Although it is not always, right? Why? Because we have to check two more properties. It's not only consistency. Agree? It's not only consistency, but yes, at least one exam we have passed. Yes. So please be clear, those who wants to work in this dimension, in this domain, in numerical methods, whenever you, so what are the research problem here, right? Those who are interested in research problem, I must tell. So what are the research problem? That you may develop a new scheme, right? Usually people do that, develop a new scheme, new numerical scheme, right? You read somewhere and then you thought of some idea and you develop a new numerical scheme, right? So how will you ensure that your numerical scheme is useful for any equation, maybe for heat equation only, maybe? So try to understand that you have to prove its consistency, right? you have to prove its stability, and you have to prove its convergence. If you can prove, then you can develop any new numerical scheme, and that will be a good contribution. And how will you prove consistency? This is the simplest idea using Taylor series expansion. Whatever the discrete version you have taken, just expand it, and there will be some terms of delta t delta x square. If you keep delta t delta x square as 0, I mean tends to 0, your discrete version should converge to the continuous version in the layman sense. And definition also I have provided, right? I have also provided you the definition. There is another way of proving consistency in norm, actually, right? So I think we should not go, I mean, because we have limited time, we have to do many things. So consistency is comfortable. Now we should see the stability. This is, I think, the most crucial thing, right? This is the most crucial thing for our numerical method, that whether our numerical scheme is stable or not. So let me tell all the participants, those who have joined. So we are going to do, we have read finite difference method. It is very important to understand that is it always going to work, or it is not going to work? Is it going to give us result, or it is not going to give us result? So those things, it is important, right? In tomorrow's lecture, or maybe if we get time today, then there we will do implementation of Black-Scholes, because we have already done implementation of heat equation. So implementation of Black-Scholes PD will also go on the similar lines, right? So in tomorrow's lecture we can do that, but before that we should have a clear picture in our mind about finite difference method. That okay, whether it is going to help us or not, we should know it, right? So we realized, and if we get time today, we'll do this today itself. Okay, so now we are going for stability condition, that okay, whatever the equation, I mean whatever the numerical scheme we have defined, whether it is stable or not. Believe me, there are so many varieties of definitions of for stability, right? People, whatever I'm going to give you, it is one, and then you can find in any book, there are so many, right? One Neumann stability analysis, matrix method stability analysis, normal mode, so many, right? So our aim is not here to understand the whole list, but our aim is to understand the key idea behind it, right? Okay, so for any initial value problem, so next is that for any initial value problem, what is the condition for stability, that is we are going to do. Okay, so idea is that so next is stability, right? So I'm not going in much detail, please do understand. The reason is simple, that we don't have that much time, but yes, uh, for any initial value problem, right? For any initial value problem, we have seen what we have seen. Please see, we have seen that once we discretize the equation, we get this kind of differences, some vector a and un, where n is greater than or equals to 0. We start from 0, right? And here u and these are vectors, isn't it? This is also a vector, this is also a vector. I hope everyone is comfortable. Now let me go back. So here you see, yes, you see here. Did you see? This is also a vector equals to a times that vector. Everyone? Everyone, right?
Yes, sir.
Yeah, please. Anyone is asking something? Anyone is asking something? Okay, anyway. So the idea is, we know that the difference scheme, we get the difference scheme, we get the difference scheme of this form, right? Right now, because so try to understand, try to imagine it, right? We have heat equation, we discretized it, and we got the discrete equation of this form. And then what we do? We implement this in MATLAB and we get the solution. Agree? So once we put n equals to 0, we get u1, then u2, then u3, then u4, right? Agree? And this is a vector. That means it is a vector containing the solution at all x. At all x. Agree? So basically what it is, u1 is what? The solution at all x. u2 is what? The solution at all x. u3 is what? Above the solution at all x. Agree? Right? So we get this kind of matrix form for our difference scheme. Now the question is when you will say that this scheme is stable. Question is, when do you say that this is scheme? Whatever you have defined, right? We have defined some scheme. And please try to understand, we are going to get the numerical solution from this scheme only, isn't it? We are going to get the solution from this difference scheme only. And we are not sure about that solution, whether it will be correct or not. So we have checked that this scheme is consistent. Now we are checking whether this scheme is stable or not. Okay, now we are checking that this scheme is stable or not. Okay, so as I said that there are lots and lots of varieties of definition of stability. So I'm giving you one. You can, if you are really interested and you are working in this numerical methods, you can explore that from that book or from any other literature. Okay, so the difference scheme, basically the difference discrete version, right? The difference scheme, which one? This one. Maybe this is equation number 2. The difference scheme 2 is said to be stable with respect to the norm, right? So any norm, right? If there exist positive constants delta x naught and delta t naught, right? And non-negative constants k and beta, so that what happens? So that norm of un plus 1 is less than or equals to your norm of u0. u0 is what? Your initial condition, right? The value of that solution at t equals to 0, right? And k e to the power beta t for any t, right? Any t, and delta x is less than delta x naught and delta t is less than delta t naught, right? So the idea is simple, that our solution is not allowed to grow arbitrarily. It's not like your solution at time level n is somewhere this, and time level n plus 1 it is very high difference from time n. So the solution should not grow arbitrarily, right? So if this condition is satisfied, we say that our scheme is stable. Now I'll spend some time here to explain you. As I said that many times here people do not take e to the power beta t. They simply take k only. Right? That is also perfectly fine. There is not a problem. But we don't need to understand. I mean, we are not going that how many definitions of stability are there. No, We are not going to. We are trying to understand that yes, if we can prove the stability, right? If we can prove the stability, then we are sure that, oh, great, our numerical method is consistent also, and our numerical method is stable also. So two characteristics, if we have proved, then we are done. Okay, so we are done. Everyone, right? So of course, this is not easy job to prove this, right? It is difficult to prove stability many times. Okay, so how will you prove it? That's important. So anyone heard of von Neumann stability analysis? Anyone heard of von Neumann? Which type of? Yes, you define any norm, L2 norm, maybe you can define simple, right? Infinity norm, maybe you take infinity norm best. Are you aware of this L2 norm and infinity norm? Yeah, so that you can take any you can simply take maximum norm, infinity norm, right? Not an issue. Actually, we don't have time, but I just request that you can simply uh, I mean, look at this book by J.W. Thomas, and then you can see there are a lot of examples there, and you can see that how to prove the stability in infinity now. Okay, yeah, okay, Adit. So I hope it is clear, Adit. You can take simply infinity now, no issue. That's why they have not restricted the norm, right? They have not restricted the norm. They said any norm you can. Yeah, thank you. So these are a bit theoretical aspects. I do understand that some of you might not feel very comfortable, but it's okay, right? So, but yes, we understood that yes, there is one property called consistency, one is stability, and the last one is convergence. So convergence, by virtue of word, actually it is saying something. What it is saying? Convergence. I mean, don't you think it says something, right? So convergence means, simply, the idea is that whatever we found the solution, right, it is converging to the actual solution. Actually, this was our target, na? This was our target. Agree? So, what was the idea? That if our solution, whatever we obtained, it is converging to the actual solution, then we say the method is convergent. Okay, so here maybe I can give you the definition in terms of norm, right? Or maybe I can give you the definition in terms of pointwise also, anyway, right? Although these are a bit tough concepts. So now the last one is convergence. But my primary objective is to brief you about this and to ensure that, okay, if you are defining any new scheme, you should be able to understand that these three properties we have to prove for any new scheme before using it, before relying on it at least. Using it's okay, but before relying on it, okay, that, oh, our method is 100% perfect. No, you have to check these three conditions before relying on it. Okay, I hope I'm clear, right? So the idea is simple. Let me write the definition at least first. So a difference scheme, it's simple like you know uh, consistency, but not exactly right. Please be clear, right? A difference scheme, any scheme which you have defined. Difference scheme means for continuous version, you have written down some discrete version. That is right. A difference scheme L K N UKN equals to GKN. Basically, you write when you write a difference scheme, what you write? You write in terms of UN plus 1K minus UNK. So that we are denoting by LKN, UKN, GKN, right? So if you are not comfortable with this notation, you understand it like it is simply whatever is your difference scheme. But we are writing the difference scheme in this format. That's it. A difference scheme approximating the PD LV equals to F, right, is a pointwise convergent scheme if for any x and t as k delta x n plus 1 delta t converges to x comma t, our UKN converges to V as delta x delta t tends to 0. So in very simple language, please do not be confused. In very simple language, what it is saying that pointwise convergence, that at any point x t, right, that is k delta x and plus 1 delta t, right? So at any point x comma t, if your numerical solution is converging to your actual solution. So suppose this heat equation, right? We know the exact solution. We know the exact solution, right? And what we are uh, understanding from this definition, this as we are taking more and more number of grid points, we have taken only 5 points. Suppose we take 5,000, we take 50,000. So as more or more number of grid points we will take, our delta t delta x will go to 0. All of us agree with this, right? Our delta x delta t will go to 0. And then if you find the numerical solution, that numerical solution should be close converged to actual solution. And it's not only at 1 point or 2 point, it should be at all points. So let us go to that figure. Let me try to explain you, right? So suppose this is the figure, right? And suppose we are interested in the solution at this point. So what will happen? We will reduce, we will increase number of points from 0 to 1. Maybe we will take 1,000 points, and we'll take 2,000 points in time. Okay. So then we will reach to this point. But when, and then you'll find the numerical solution at this point. Numerical solution at this point. Agree? Now, when you will say that your scheme is convergent, when do you say? You will say your scheme is convergent when whatever you obtained numerically, and we can compute it exact solution also, because that we know here. In this case, we know, right? We know exact solution. So we saw that when we took 100 points, then our numerical solution is close to exact solution. When we take 1,000 points, 1,000 point means delta x and delta t tends to 0. Agree? More small. Then we saw that our numerical solution is even more closer to the numerical exact solution. So as delta t, delta x are going to 0, right? As delta x, delta t are going to 0, right? What happens? Our numerical solution is approaching to the exact solution at any point. It's not only 1 or 2 points. If this is the case, then we are clear that our scheme is convergent. And there are various ways to prove all these three properties. Actually, without these three properties, finite difference scheme is a bit incomplete, I would say. Right? A bit incomplete. That's why we try to do this. Uh, this gives us at least. So, what is the conclusion? What is the conclusion? Uh, Conclusion is that if we define it, there are various numerical methods, right? I discussed in the I mean, I think day before yesterday only that we have lot many numerical methods. So which one is suitable for you? This also uh, can be obtained from these three properties. Suppose I have a partial differential equation. I want to solve it using finite difference method, but then we realized, oh, whatever the scheme we defined, it is not consistent. Then it is of no use. Then whatever the scheme we have defined, it is consistent but not stable. Then also it is not useful. Then we realize that, oh, we defined a scheme, it is consistent, it is stable, but it is not convergent. Then also it is not useful. So in this way, it helps us to choose the scheme for our problem uh, from the variety of schemes. We can choose the best one, best suited for our problem. Right? So this is, I think, the most fundamental thing which we have covered. Only thing we have to cover only two more things, right? So uh, I mean, how you choose different schemes, right? Okay, how you choose different schemes, that we will discuss a bit maybe, and then we will go for MATLAB. Okay, so but before that, I'll show you some power of mathematics actually, right? So what is the power of mathematics? Lax equivalence theorem. I said the power of mathematics, right? Right. So please read this carefully. A consistent for initial value problem. For initial value problem. Okay. A consistent two level means n and n plus 1. There are only two. In the scheme, there is n, there is n plus 1. It is not n plus 2 or n minus 1. Right? So in the scheme means you have un plus 1 equals to aun. Two level difference scheme. Two level difference scheme. I'll give you the example, don't worry. Two level difference scheme. For example, we have seen this un plus 1 equals to aun. Okay. Scheme for a well-posed problem, well-posed linear initial value problem. It is beautiful result. And anyone from the audience can I mean, did you hear it earlier? Post linear initial value problem is convergent if and only if it is stable. What it says, let us try to understand it. What it says, that if you have this kind of difference scheme, what kind of difference scheme? Un plus 1 equals to aun. And from where it is coming? It is coming from a partial differential equation initial value problem. Initial value problem means you have equation and you have initial condition, right? You have equation and you have initial condition. Okay, agree? So you have equation and you have initial condition, and for that initial value problem you define the scheme when it will be convergent. Suppose it is consistent. It is given that it is consistent. So what this lax equivalence theorem says? What this lax equivalence theorem says? It says that if it is stable, consistency is clear, but if it is stable, then it will be convergent. That's it. Wow, that means what? we have to only prove, for such kind of problem, we have to only prove two properties. Third is automatically done. So what we realize, that's why I said, no, this is the power of mathematics. What is the power of mathematics? Simple idea is that if it is consistent, consistency is important. Right? Consistency, you cannot relax. If it is consistent, then it will be convergent if and only if it is stable. What does it mean? If we prove it is consistent and if we prove that it is stable, then we do not need to prove stability, convergence. Then we do not need to prove convergence. Why? Simple. The simple idea is that we can simply use Lax equivalence theorem. Lax equivalence theorem says that it is simply assures that if it is consistent and stable, right, it will be convergent. All of you agrees with me that this one theorem tells you that only two properties you need to prove, no need to go for. Okay, so till here we discussed the consistency, stability, and convergence of finite difference schemes. So now we have a better picture in our mind. What is the better picture? That yes, we have a heat equation and we defined a numerical scheme, right? We defined a numerical scheme and then we solved it by with the help of system of linear equation by writing it into the matrix form. But and we are going to get the solution from there. But who guarantees that whatever the solution you are getting, that is accurate solution? Who guarantees? These three conditions. We have already proved that our scheme means what? This, please do not be confused. Scheme means this equation number one. So you will prove the consistency for this scheme, you will prove the stability for this scheme, and you will prove the convergence for this scheme. If you are doing these three conditions for this, and suppose you are able to prove, these three things for this, then it's done. I mean, you don't need to worry that whatever the solution you are going to get, that solution is accurate, right? That solution is accurate. Everyone, okay? So till here we have done. Now the question comes that if our scheme is not consistent or not stable, then what should we do? This is also a question, na? Then what should we do? So here we'll go in brief the most popular, I would say, the most popular time discretization methods in very quick. I'll not take much time there, right? Very quickly, I'll go that three time discretization methods. I believe that if you are reading finite difference method, you must know those three methods, right? At least you have some idea, because now you have some idea about consistency, stability, and convergence. On the similar lines, you should have some idea about that what does it mean by forward Euler, backward Euler, and Crank-Nicolson. So now what we are going to do, first of all, try to understand the motivation. The motivation is, suppose our scheme is not consistent or not stable. Whatever we have defined, suppose our scheme is not stable, then what should we do? The simple answer is we should change our scheme, right? We should change our scheme. So how people have done it in earlier times, right? How did they change? Of course, there are many change possible, but I'm trying to tell you the most popular one, three methods. Those are very well known and very much useful in literature, very much used in literature. So let me give you in the way that what we discretized. Can you quickly recall that Vkn plus 1 minus Vkn upon delta t equals to vk plus 1n minus 2vkn plus vk minus 1n upon delta x square. This is one. This we have been doing. Let us suppose, I'm not going in detail, right? Let us suppose this is not convergent. So what people did that equation is same. They just changed a bit. What did they change? They take that, okay, vkn plus 1 minus vkn upon delta t equals to vk plus 1 n plus 1 minus 2 vk n plus 1 plus vk minus 1 n plus 1 upon delta x. Can anyone quickly realize what the difference in it from earlier? Can you quickly realize, anyone? What is the difference from earlier? The difference is simple, that in the right hand side we put instead of n we put n plus 1. We put n plus 1. Agree? So then people realized, oh, this is also not very good. What are the problems in this? I'll not go in that detail, right? Maybe at the end I'll tell you that, okay, what is the problem here, what is the problem in this scheme, why we are going. Then people did another scheme also. People modified this two and they provided another scheme also. So we are doing it here for heat equation. Please be clear, right? We are doing it here for heat equation. Let me name it, then you may feel a bit interesting. So this is called forward Euler. I'll tell you why it is called forward Euler. Right? Forward Euler scheme. This is called backward Euler. Right? Called backward Euler. Another one is called Crank-Nicolson. Please be clear. Wherever we have in mathematics, wherever we have choice, that means no one is perfect. That's why we have a choice, right? We are going to buy a car. If any car is perfect, why we should have so many cars, right? So in the same way, if we are going to apply some scheme for some PD, if suppose some scheme is perfect, then we don't need to go for any other scheme, right? So what it clearly tells us that no scheme is perfect. I'll tell you a bit about all these schemes, at least for heat equation. Okay, is for heat equation. So what Crank-Nicolson says, Crank-Nicolson is, don't be confused by Crank-Nicolson, etc. What did they do? They said that, okay, you take this average of about 2. What did they say? They said you take average. That's why you divided by 2, right? So they said that you take average of about 2. Now, the very first question, why we have been taught these 3 schemes? Let us do question and answer one by one. The very first question is why we should read these 3 schemes. Answer to this is simple, that the first one is not perfect. Now let us see why it is not perfect. I'll not go in mathematics to tell you that how to prove that it is not perfect, but let me tell you that this forward Euler is saying that it is not stable always. Did you get my point? It is saying that it is not stable. So once you derive the stability condition for this scheme, you will realize, oh, it is not always stable. That means what? It is conditionally stable actually, right? So it is not always stable. That means what? Oh, sometimes it may not give you the accurate results. Did you get my point? So it is not always stable, right? It is not always. Then people went on this backward dialer. It is always stable. Wow, great. But then why went for Crank Nicholson? Got it? See, I'm trying to pose as many questions as possible in this short duration to you, those who are who wants to work as a project in this dimension, or who wants to work uh, as a research scholar in this dimension. This would have this clarity in their mind that if this is always stable, this is always stable, then why we are going for chronicles? Question is clear, right? It is always stable, we are happy, but then why we are going for chronicles? Okay, so the answer is that it is slow. What does it mean by slow? That whatever the solution it is giving to you, it is slowly converging to the accurate side. It is not very fast giving to you the accurate. So please try to understand that suppose you have exact solution for this heat equation. Suppose the exact solution value is 5. Then this, if you obtain your numerical solution from backward dialer, it will give you suppose 4.8, then 4.82, 4.84. I mean, it will, and how it converges once you make a smaller delta t delta x, right? We have read that, but we have read that if you take a smaller and a smaller and a smaller delta x delta t, your numerical solution converges to the exact solution. The question is that how fast it converges. So here I'll discuss one more point. So if you are defining any numerical method, right, what are two key properties you wish? What are two key properties you wish? Let me tell you, right? Just 1 minute. So key properties are accuracy, of course, and efficiency also. It's not like, oh, it is giving you accurate solution, but it is taking 2 days of time. It does not make sense. All of you, right? So efficient, how fast the algorithm is, how efficient your algorithm is, that is also important. Okay. So whenever you are developing any numerical method, you should be careful that your method should be accurate and efficient. Efficient means it should be fast enough to provide you the solution. So one advantage, one disadvantage for forward dialer. For forward dialer, it is very easy. We have seen it is easy to implement, but not always stable. Clear? What is the advantage and disadvantage of backward dialer? It is stable, advantage, but what is the disadvantage? It is complex, difficult to implement, easy to implement, right? It is not, a bit complex. I'll tell you by geometry also why it is complex. I'll tell you by geometry, but it is a bit complex. And another way why, that's why it is slow actually. Why it is slow? It is a bit complex. When it does the job in MATLAB, I'll show you, it is a bit complex. Okay, so then we went for Crank-Nicholson. What we realized that, oh, this is fast. Advantage is this is fast, right? Stable also, mostly, right? Stable hai, fast. But then what is the problem? Then we should always go for Crank-Nicholson. Actually, that's why it is most used as compared to forward dialer and backward dialer. Klein-Nicolson is mostly used that because the reason is it is fast also. Fast in the sense that you will reach to your exact solution quickly as compared to backward dialer. You will reach to your exact solution quickly as compared to backward dialer. And it is stable also. No, consistent are all. More consistent doesn't mean anything. Jai Kishan ji, see, try to understand. It is not more consistent or less consistent. Either it is consistent or not consistent. So Jai Kishan, understood? So all these are consistent. There is no problem with the consistency. If they are not consistent, we won't discuss it here at all, because if scheme is not consistent, doesn't make sense. I mean, we should not use it at all. Okay, so consistent is okay, but I'm just trying to give you the picture that okay, you designed a scheme, you designed a new scheme, and it is very easy, but it is very slow, then it is useless. It is very difficult, but it is not giving you the accurate results. It is very slow, then also it is very useless. So I'm trying to create a permutation combination to you that you have to understand both the aspects. For you, it is, suppose you try to understand that suppose you have to predict the rain, and you implemented in your computer, and your method is too slow that you are predicting the rain tomorrow, but your computer gave you the result day after tomorrow. Is it useful? Not useful. Agree? So you have to, while designing a numerical scheme, you have to be careful about accuracy as well as efficiency. Mr. Jakishan, everyone, those who are interested, at least it is clear to you that right, that you have to be careful about both the things. Okay, now, so then what is the problem for Crank-Nicholson? That it becomes it gives oscillation in solution in certain cases. In some cases, it may give you oscillations. Oh, that is a problem. So why I told you the last one? Because none is perfect. You should not think that, oh, Crank-Nicholson is always too good. Why to go for backward or forward or? No. Answer is simply no. That, oh, only Crank-Nicholson is used. No. Okay. So yes, it is fast, but it may also have problems sometimes. So those who wants to work in this domain, they can simply understand that all these and these three kind of numerical schemes are most popular: forward dialer, backward dialer, and Crank-Nicholson. So what we did in these three schemes, please, if you want to differentiate, in one forward dialer, we take the space derivative, the derivative, second order derivative at nth time level. In backward dialer, we take the second order derivative at n plus 1th time level. And in Crank-Nicholson, we take the second order derivative at nth time level also and n plus 1th time level also, and we take that away. I hope I'm clear. How do you define this forward dialer, backward dialer, and Crank-Nicholson? Right? So now it is your choice that which scheme you want to go. If you don't want any oscillation, you are okay with slow, go for backward dialer. If you want fast method, go for Crank-Nicholson. If you want very easy to implement, right? That's why I told you forward dialer only, because it is easy to implement. You see what we did? We did forward dialer. You see here, it is here N only. This is here N only. So this is nothing but forward dialer. Right? If you want very easy scheme, you go for forward dialer. So I hope I'm clear. Let us understand it by geometry and then we will wind up. And this much we will do in finite difference. That's it. We will not go much more. In the next lecture, we'll first understand it by geometry also, and then we'll in the next lecture we'll do MATLAB first, and then we will do how to implement Black-Scholes PD for in using finite difference method. How to solve Black-Scholes PD using finite difference method. Right, this is our ultimate goal. And day after tomorrow, I have one lecture. There we will do some machine learning aspects for uh, option pricing problems. Machine learning aspect for option pricing problem. All good. So now let me quickly tell you the geometry actually, right? For all these three. So let me write it: forward Euler, backward Euler, and triangle constant. So what is geometry? So let us try to understand this and this. So this is known, this is known, this is known. We all know, right? Initial and boundary conditions. And then we must try to, again, like I'll take only 3 points so that it will be clear to you, right? Just for simplicity, right? So, right, we want to find the solution. Let me take another color. We want to find the solution here, here, here. Okay, everyone? Okay, so tell me, in forward Euler, suppose this is point, this is A, this is B, this is C, this is D, this is E. So we have seen to find the solution, we use A, B, C, D, E. Are you convinced, everyone? We have seen yesterday. To find PQR. This is PQR. This is the this is P, this is Q, this is R. Are you convinced? Jai Kishan, Aditya, everyone. Yesterday we saw that if we want to find PQR, we need A, we need B, we need C, we need D, we need E. Yes? But what about backward Euler? So in backward Euler, actually this will be on the left hand side. So here you need to invert a matrix. You need to invert a matrix. What does it mean? That you need B, C, D, and maybe this is F, this is G. F and G, it is known, right? I'm making dot point there, those are known. So here you need F and G. You need B, C, D, F, G. Agree? And here you have to invert a matrix also. That is also a problem. And here what you need? Here you need everything. Right? This A, B, C, D, E, F, G, everything. And here also you have to invert a matrix. What does it mean by invert a matrix? Let me explain it. Right? So in forward Euler, what the equation you get? Un plus 1 equals to AUN. No need to invert. You have Un. You multiply by A, you get Un plus 1. In backward Euler, what you get? AUN plus 1 equals to UN. So if you want to find UN plus 1, what you need to do? A slash UN. So invert, you have to invert it. Agree? You have to invert it. Agree, everyone? And last, after that we will wind up. Uh, for Crank-Nicholson, what you will do? This is backward LR. Please try to understand. For Crank-Nicholson, you get AUN plus 1 equals to BUN. That means UN plus 1 equals to A slash BUN. So don't you think here more operations are involved in Crank-Nicholson? So this is the key idea of all three methods, uh, forward dialer, backward dialer, and Crank-Nicholson. It is easy. It is clearly, we can see from here, right? We can see from here, isn't it? Forward dialer. Nothing to do. Just multiply A by U, you'll get it. We did it, MATLAB. If you remember, we did yesterday. In backward dialer, you have to invert one matrix, and in Crank-Nicholson, right hand side also there will be a matrix. So you have to first multiply B and U, and then you have to invert. So it's clearly complicated. There is no doubt about it. Agree, everyone? So we will wind up here today what we understood in this second lecture. I mean the lecture today on day 3. On day 3, that I told you one book by MathWorks based on MATLAB. We recap that how we can be sure that the solution which we are getting is correct. That is a big question, that how you are sure that whatever you are getting is a correct, right? You should have some proof with you. So we realize that yes, we have proof because we proved that our method is consistent, our method is stable, our method is convergent. If we can prove these three properties for our scheme, we are sure mathematics guarantees that yes, your solution is perfectly fine. No need to worry. Then we did one Lax equivalence theorem that it says that if you have consistent and stable scheme, no need to worry about convergent until under certain conditions, that it is a two-level scheme, etc., etc. But still, it guarantees that okay, no need to worry about convergence. All good till here? Then I tried to show you that how people modify and how people get different schemes. How people get different schemes. And I told that there is something called forward dialer, there is something called backward dialer, there is something called Crank-Nicholson. I gave you advantage and disadvantage of all those schemes. What are the? Every scheme has its own advantages and its own disadvantages. We discussed in detail. I tried to give you its geometric interpretation and matrix interpretation also, right? So I hope you enjoyed all this, whatever we have done today. If you have any queries, you can ask. Otherwise, we can wind up here. And please note that next lecture is scheduled at 11:30 Indian time.